And now we'll screen share, the usual thing. Share. Right, let's take care of this. All right, let's focus that. Right, maybe brighten it up a little bit. There we go. Okay, so with some fortune, as it turns out, we don't need to review too much. Not if you were there last time and remember what we were doing. So let me go through it. We basically worked out the equation, the Dirac equation for a free particle, free relativistic particle. It's first order in space, and also space over here is spatial derivatives, and also first order in time. It involves a wave function, which is understood to be a 4-component spinner. We decided it had 4 components after a while. It's got matrices alpha, a vector of matrices alpha, and a scalar matrix beta, which take part in the equation like this. The right-hand side can be written as a Hamiltonian multiplying by psi, where the Hamiltonian is what you see in the parentheses here. Alpha dot p is a product of a vector of matrices, now 4-dimensional Dirac matrices, dotted into the usual momentum, 3-dimensional momentum. And then MC squared beta, beta is this constant matrix here. We determined also the form of the matrices alpha and beta. Alpha is a sigma Pauli matrices on the off diagonal, and beta is 1 minus 1 on the diagonal. This is partitioning Dirac matrices, 4x4 matrices, into 4 2x2 matrices, which is what we'll normally do in representing Dirac matrices. This gives us what we call the Dirac-Pauli representation of the Dirac algebra. The Dirac algebra can be written as a set of anti-commutation relations, which have to be satisfied by the alpha and beta matrices in order that every free particle solution of the Dirac equation up here should also be a solution of the Klein-Gordon equation. The alpha and beta matrices satisfy a number of properties. They're, in the first place, they're Hermitian, in addition to these anti-commutation relations, but they also have the property that if you square any one of them, any of the alphas or the beta, you get 1. So all of them square to unity. And I think that basically takes us up to where we left off at the end of the hour last time. And I'd like to ask before we begin if there's any questions about that. If not,
I have a question.
Yes, question.
Is it ever useful just to multiply this equation through by beta, because then it's like there's a matrix in front of every derivative or something like that?
Yeah, there is, and we'll do that a little later on. But this is considered the Hamiltonian form, because in Hamiltonian mechanics, the Hamiltonian is the energy is IH bar ddt. That actually goes back to de Broglie's, wave formula, his plane wave and the Einstein relations. So the IH bar ddt must be related to the Hamiltonian, and that's what this is on the right-hand side. All right, but the suggestion you're making is something we'll actually do, not this lecture, but maybe the next one after that. All right, so the main problem with what we've done so far is that free particles are fairly trivial and kind of boring. So it's of interest to include the interaction with the electromagnetic field in order to get a more non-trivial problem. We're going to do this by the method of minimal coupling, which I'd like to now explain. So let me take this summary sheet away and replace it with a fresh pad here. And I'll tell you a little bit about minimal coupling. So the idea of minimal coupling can be motivated strictly within classical mechanics, and that's what I'm going to do. Here's the idea, is that if we're talking about relativistic classical mechanics, and we want a Lagrangian for a free particle, let me call it L0, the Lagrangian for a free particle. One way to write it is this, is the square root of the metric tensor G mu nu multiplied times dx mu d lambda times dx nu d lambda. And the idea here is that you've got space-time, so here's the space-time here, the spatial coordinates, and there's a time here. And you've got a whirl line, which is passing through space-time of a particle. It's got x mu, which is parameterized by a parameter lambda along the whirl line of the orbit of the particle. And so these are derivatives, these are basically whirl velocities computed with respect to the parameter lambda. This Lagrangian gives rise to the correct free particle orbits, which of course are just straight lines. They also happen to be geodesics of the metric, and that's what this free particle Lagrangian gives you. Now let's suppose in addition to the free particle Lagrangian, we know about the electromagnetic field. We know about the vector 4 potential A mu, which in 3+1 form is phi and A vector like that. We know about the field tensor F mu nu, and there's various higher order tensors too one can deal with, such as the stress energy tensor that can be constructed out of the F. What we'd like to do is to write down an interaction Lagrangian, which will give the interaction between the otherwise free particle and the electromagnetic field. Now, the strategy is the following. We say that in relativity theory, we require that the equations of motion be Lorentz covariant, that is, that they have the same form in all Lorentz frames. And that result will be guaranteed if the Lagrangian, which generates the equations of motion, is a Lorentz scalar. This L0 for the free particle is already a Lorentz scalar. It's just the scalar product of the world velocity with itself, the square root of that. In order to create an interaction Lagrangian, which is a Lorentz scalar, we don't actually have too many choices. We have to combine together some vector or tensor-like quantity connected with the particle with something connected with the field. Well, the simplest vector connected with the particle is just the world velocity, dx mu d lambda, taken with respect to our arbitrary parameter lambda that I introduced up above. And this is really all we've got to work with, considering in terms of the particle degrees of freedom. I mean, you could go on to higher derivatives if you want to, but usually Lagrangians don't depend on higher derivatives, just the first derivative. So in any case, if you limit it that way, then this is really all you've got for the particle. Now then, the field has got various tensors, A mu, F mu nu, and so on. The simplest scalar that can be constructed is to take the contraction between the vector 4 potential and the world velocity of the particle. And so if we postulate that the interaction Lagrangian is proportional to this, this is called minimal coupling because it's the minimal in the sense of being the simplest Lorentz covariant, or it's a Lorentz invariant Lagrangian interaction, which will give rise to Lorentz covariant equations of motion. And if we do this and we add L0 plus L int, it turns out you need to use the prefactor Q over C, which Q is the charge of the particle, dx mu d lambda, like this on A mu, if you want to get the correct equations of motion for the interaction between the field and the matter. This isn't the only Lorentz invariant interaction Lagrangian we could have written down. We could have taken, for example, the stress energy tensor, which I didn't write down here, T mu nu, and sandwich dx mu around the two sides of that. It won't do to try that with a field tensor because the field tensor is antisymmetric and the result will be 0. But there's higher order tensors you could use. So this is not the only coupling. As I say, it's just the simplest one, and therefore it's what they call the minimal coupling. All right. So using the minimal coupling, we actually do get the correct equations of motion in the sense of being the Newton-Lorentz equations of motion. Now, when you convert this Lagrangian into Hamiltonian, what you find is that the momentum, the p mu, then, is equal to the mass times dx mu d tau, where tau is a proper time. That comes from L0 alone. And then what you get is a plus q over c times the vector potential A mu coming from the interaction. And so if the part coming from L0, this is the form momentum for the free particle. And this is represent, so anyway, so this is the replacement one needs to make to go from the, let's call this P0 mu, the first term, to go from the free particle to the momentum in the presence of the field. All right. So what this means is a practical matter. If I take a Hamiltonian such as H for the Dirac Hamiltonian, which is equal to C times alpha dotted into P, like this, plus MC squared beta. What I should do is I should make the replacement P mu goes to P mu minus Q over C A mu. Because you see the P that appears in here is really the P0. It's really this part. And that solving for this, you see it's the total P minus A. So making this substitution, well, this is a 4 vector. If I break it into its space-time parts, the energy, which I'll call H, goes into H minus Q phi. Because you see the 4 vector potential A mu has components phi and the three vector potential A like that. And then the 3 momentum P goes over into P minus Q over C times A, the vector potential. And if we do this and I write H goes to H minus Q phi and then bring the Q phi over the other side, then this turns into H is equal to C times alpha dotted into P minus Q over CA plus Q phi, which came from the transformation on H, plus MC squared beta. And let me box this because this is the Dirac Hamiltonian for a particle now interacting with an external. This is an external C number electromagnetic field. It's not quantized, but it's an interaction with the external electromagnetic field specified by the potentials phi and A. You can kind of see that the Q phi is the same as the potential energy that would appear in the Schrodinger equation. And you can see that the P minus Q over CA is also something that appears in the usual Schrodinger equation, but there it's squared. And here it's multiplied by the vector alpha spin matrices, which I displayed on the last page. Likewise, here's the MC squared beta, which occurs already in the free particle Hamiltonian. So it's a guess that this is the correct Hamiltonian for our Dirac particle interacting with an electromagnetic field. And we'll test this guess by exploring the various properties of this Hamiltonian and seeing if it makes sense. That's just what Dirac did. So the first task that I'd like to address then is the question of the probability density in current. Let me remind you that in the case of the Klein-Gordon equation, we found a nice probability density in current, rho and j, which could be assembled into a 4-vector, which actually genuinely was a 4-vector, and moreover was conserved in the sense that 4 divergence is 0. But the problem is that the so-called probability density wasn't positive definite, and so actually couldn't be a probability density. That was the problem with it. Let's see what our luck is like in the case of the Dirac equation. I'm going to work this out by writing out the full Dirac equation as a differential equation. So the left-hand side is I h bar d psi dt. And for the right-hand side, I'm going to first take the C alpha dotted into P. So this becomes P is minus I h bar. So it's minus H bar gradient. So it's minus I h bar C times alpha dotted into the gradient of psi. That's the first term. And then we get C and Q over C cancel. We get minus a Q times alpha dotted into the vector potential A, multiplying onto psi. Then we've got plus Q times the scalar potential capital phi multiplying onto psi. And then we've got the plus MC squared beta multiplying onto psi. So this is just the Dirac equation in the presence of an electromagnetic field, following our assumptions, just written out explicitly. Now then, let's realize here that's a remind ourselves that psi is actually a 4-component spinner. We don't yet have an interpretation for what these 4 components mean, but we're going to be working towards that. We'll find out some information about them in a little while. But anyway, the psi is such a spinner. And I'll remind you also that the alpha here that appears there, and the beta there are 4x4 matrices that act on spin space. The alpha is a vector of such matrices. Given the psi, then this is what you can call the column spinner. You can create a complex conjugate row spinner by calling it psi dagger, which is psi 1 star through psi 4 star, like so. And if we take our equation that I just wrote down and I multiply through by psi dagger from the left-hand side, like this, going all the way through, what this will do is this is a spinner equation that's written out, but by multiplying by psi dagger, it will get rid of you'll get rid of all the spinner indices, and you'll end up with something that's a scalar insofar as the spin degrees of freedom are concerned. Something is a scalar in spin space, if you want to talk about it that way. So allow me to do that and write out the equation. This is basically following the same procedure we used in the Schrodinger equation to work out the probability density and current. If I do that, the first term becomes IH bar psi dagger times partial of psi with respect to t. In the right-hand side, I get minus IH bar C constants. And then we get a psi dagger multiplying times alpha dot gradient psi for the second term. Then we get minus Q, and then we get psi dagger psi sandwiched around alpha dotted into A, the vector potential. And then the next term is plus Q phi times psi dagger psi. Notice that phi is a scalar potential, so it's just a function of position, and it doesn't have any spin indices. So it's really a scalar insofar as the spin indices are concerned. That's why I can pull the psi dagger past it and just end up with a scalar product psi dagger psi. And then finally, the last term is mc squared, and then I get psi dagger beta psi. I hope I have room to write it here, and I hope you can see it. But that's the last term, mc squared psi dagger psi sandwiched around beta, like that. All right. Now the next step then is to take the Hermitian conjugate of this equation, or rather, excuse me, let's take the complex conjugate of this equation. Because every term in this equation is a complete contraction in spin space, we get the complex conjugate by reversing the order of the spin operations, row and column spinners, and daggering everything in the process of doing it. So for example, the first term turns, and of course you complex conjugate the coefficients. So the first term is minus IH bar, and then I get partial psi dagger with respect to t times psi. You see, reversing the order here and daggering things. On the right-hand side, the next term becomes plus IH bar c, and then I get a psi dagger, excuse me, I get a gradient psi dagger dotted into alpha. Let me put it like that, multiplied times psi. That's this thing running backwards, you see, in daggering things. And the next term is minus q, and running this backwards, I get psi dagger alpha dot psi, alpha dot a, excuse me, times psi. Running this thing backwards doesn't change it because the psi and psi dagger just exchange places. The a is a spin matrices, which ought to be daggered, but it's Hermitian, so it doesn't change it, so it just turns into itself. And the a here is the vector potential, which is a C number, a real C number, so it doesn't change either. Then moving on to the next term, we get q times phi, psi dagger psi goes into itself. And then the next term becomes plus mc squared, and then psi dagger beta psi goes into itself also upon complex conjugation. All right, so we get these two equations. Now we'll take the second equation and change the sign, so that goes into a minus, this comes a plus, that becomes a minus, and that becomes a minus there. And then we add them up. And if we do so, the mc squared beta terms cancel because they come in opposite signs. So do the q phi terms, and so do the vector potential terms. They all go away. All that's left over is the first two terms. On the left-hand side, we get IH bar, and the sum can be written as ddt of psi dagger psi. And on the right-hand side, we get minus h bar c, and then the sum of these two things can be written as the divergence of the vector, which is psi dagger psi sandwiched around alpha. Okay? Because the del dot gives you by the chain rule, it turns into these two terms using vector identities. And now the IH bar is common to the both sides. We can cancel that. And it's convenient then to write the result in the following way. Let me get it centered here. We'll write the result this way. We'll define rho is equal to psi dagger psi. And we'll define J vector is equal to speed of light c times psi dagger psi sandwiched around alpha. Okay, this is definitions then. But if we make these definitions, then what we have derived is an equation which is partial of rho with respect to t plus the divergence of J is equal to 0. In other words, we have a continuity equation. All right. Now, if we compare what we did here to what we did with the Klein-Gordon equation, and remember what the issues were, one of the issues is whether or not the rho and J, when we assemble them into a 4-vector, let's do that. Let's put them in a 4-vector here. The time component is C times rho, and the spatial component is J. Let's do that, because if we make this identification, then the continuity equation is the 4 divergence is equal to 0. Now, I said we shouldn't use this type notation with the Schrodinger rho and J because the rho and J don't form a 4-vector in the Schrodinger equation. It's a non-relativistic equation. So the first question that arises here is whether the rho and J assembled into something that looks like a 4-vector here, whether it really is a 4-vector. Does it transform as a 4-vector under Lorentz transformations? Now that question cannot be answered without knowing how the Dirac wave function itself, psi, transforms under Lorentz transformations, and that's a fairly big project, which is going to take us certainly into the next lecture to do. So I'm going to postpone that, but except I'll tell you, it does turn out that this does transform as a 4-vector. And so we get a conserved current then, which is not only conserved, but is also covariant, and a covariant conservation law. Now, what about the problem that we had with the Klein-Gordon equation, that the probability, so-called density, was not positive definite? What about here? Well, here it's psi dagger psi. So rho equals psi dagger psi. We can write it this way. It's equal to the rho complex conjugated spinor psi 1 through psi 4 complex conjugated, multiplied by the column spinor psi 1 through psi 4 not complex conjugated. And so the product then is the sum, let's call it R as an index. R goes from 1 to 4 of psi sub R absolute value squared. And you can see that this is greater than or equal to 0. And thus Dirac's program that I've been outlining here of constructing a relativistic wave equation yields a forecurrent in which the time-like component, the time component, is indeed positive definite, and therefore can be interpreted as a probability density. And having done this, Dirac was very proud because he thought he had cured one of the problems of the Klein-Gordon equation. Now, from the modern point of view, we know the story is rather completely different, and Dirac was really seriously misconceived and misled in this assumption that he made. But that was his goal, and this is how he did it. And the formulas he's writing down are actually correct. They just have a different interpretation. But anyway, for now, let's just follow what Dirac was doing and say, hooray, we've got a positive definite probability density. So this is an improvement over the Klein-Gordon equation. All right.
Professor, can I ask something quick?
Yes.
Yesterday I forgot to ask this, but at some point you mentioned something about the non-positive definiteness of rho having something to do with the fact that it was second order in time.
Yes.
I didn't really quite get that.
Well, I
how
didn't
does
go into
Dirac-
it. I didn't want to go into it because I just wanted to say that Dirac could see that this was true, and this is what motivated him to to look for something first order in time. I mean, we don't have this problem with the usual Schrodinger equation, which is first order in time. And if you compare the two and you see how the Schrodinger equation comes out of the Klein-Gordon equation in the non-relativistic limit, you can see that that's the problem. It's really second order. Okay. Anyway,
I have a question.
I think the motivation is more important than the details. Yeah. Next question.
So what happens if you but we also saw that this psi also satisfies the Klein-Gordon equation. So yes. I'm a little confused as to how do we see that the problems are gone in that case? Like if we just plugged it into the Klein-Gordon equation.
Well, you could ask what's the relationship between the rho here and the rho from the Klein-Gordon equation. I mean,
right,
the Klein-Gordon equation would have a single rho for each component. Because I mean,
I see. Yeah.
And this is a 4-component object, you see, and the J has got the alpha matrices in here, which mix up the different components. So it's not the same thing. It's not the same thing, nor is it a sum of Klein-Gordon probabilities, like one for each component. It's more complicated than that. All right. Now, recall that the other problem with the Klein-Gordon equation was that it had solutions of negative energy, and we didn't know what the interpretation of that was. So let's take a look and see if what that situation is like with the Dirac equation regarding negative energy solutions. Does the Dirac equation have negative energy solutions is now the question. So to answer that question, let's take the free particle at rest. It's the simplest possible thing we can, at rest, it's the simplest possible solution we can write down for the free particle. Free particle at rest means the momentum is equal to 0. So the Dirac equation is IH bar d psi dt is equal to C alpha dotted into the momentum P times psi plus MC squared beta psi. I'm speaking now only of the free particle equation now, so there's no electromagnetic field in this. But we'll drop the alpha dot P term if we assume the momentum is 0. And I can write this way as IH bar ddt multiplying onto psi, which is this 4-component spinor object, is equal to MC squared. And then the beta matrix has got a 1, 0, 0, -1 on the diagonal multiplying psi. like this. And this equation is easy to solve, and if we do, we find 4 solutions. We find that psi of x and t, the action does not depend on x because the momentum is 0. There's 4 solutions, and one of them looks like this. It's 1, 0, 0, 0 times e to the minus I mc squared t over h bar. The mc squared comes from here, and the t over h bar comes from solving the simple differential equation if you just write this out. Another one is 0, 1, 0, 0 times the same time-dependent factor, e to the minus I mc squared t over h bar. There's another solution, which is 0, 0, 1, 0. You see the 4 components of the Dirac spinor are decoupled in the case in which the momentum is 0, because the beta matrix is diagonal. It uncouples them. This is supposed to be a 1 here. I'm sorry. It looks messy. Then there's 2. So there's 2 more solutions. One's got this spinor multiplied now times e to the plus I mc squared t over h bar. Because of the minus sign here changed the sign. And then there's another one, which is 0, 0, 0, 1 times e to the plus I mc squared t over h bar. And I'm running out of room, and I hope you can see that. All right. So this gives us the energy then. The energy, these four solutions have energies. And the energy of the first one is mc squared, because that's, you can tell that from the dependence. It's an energy eigenstate. You see there's the dependence, typical time dependence of an energy eigenstate. The next one's got energy mc squared. It's the same time dependent factor. But the next 2 have energies minus mc squared, because the plus sign in the exponent. And so what we see is that the Dirac equation possesses solutions of negative energy, just like the Klein-Gordon equation did. And so we still have this interpretational problem, or that this aspect of the difficulty remains. By the way, if we took a look at the Pauli theory, of course, for an electron anyway, involves 2 component spinors. If we took the Pauli free particle solutions at rest, the answers are really quite simple. The spinor is either 1, 0, or else it's 0 and 1. And there is no space-time dependence. It's independent of both space and time. It's independent of space because that's the only way you can get the momentum equal to 0. And it's independent of time because the non-relativistic energy is 0 also if it particles at rest. The relativistic, and see, in relativity theory, we usually include the rest mass mc squared in an accounting of the energy. So a relativistic particle at rest has the energy mc squared. We usually throw that away when talking in non-relativistic theory. So actually accounting for this constant shift in energy mc squared to go between these 2 cases, what you can see is that the Pauli spinors at rest, or the Pauli solutions at rest, are actually the same thing as the upper 2 components of the Dirac equation. And so this indicates a connection between the solutions of the non-relativistic Pauli equation and the upper 2 components of the Dirac equation. In this special case, in fact, they're equal to one another except for the shift in energy by mc squared. On the other hand, the negative energy solutions have got components down below, and there's no analog of that in the non-relativistic theory. So we still need to interpret what those mean. Okay. All right, so those are free particle solutions at rest. All right. The next thing to do is a matter of exploring this Dirac equation to see if it makes sense. Let's take a look at the Heisenberg equations of motion. This will give us some idea about the physics of this. So let's take our Hamiltonian. I'll write it up this way: as c times alpha dotted into pi plus q times capital phi plus mc squared beta, where pi is the kinetic momentum. It's p minus q over ca, just like in the non-relativistic theory where we had problems with magnetic fields. Let me try to brighten this up again, refocus it. All right. And I'll give you the basic commutators here. The commutator of x with x is xi with xj is equal to 0, of course, so they commute. The commutator of xi with a pi j is equal to ih bar delta ij. And that's because the x commutes with a. The a is a function of x and t, so x commutes with any function of itself, and the correction term doesn't make any difference in the commutator. This is essentially a commutator with momentum. P or pi doesn't matter. And then the commutator of two components of pi, the kinetic momentum, is equal to IH bar times Q over C times epsilon ijk times the magnetic field B sub k. Now, I'm not going to derive this last commutator because I did so last semester when we were talking about particles and magnetic fields, and the derivation is the same. Plus, there was a homework problem on it too. So I'm assuming you have some memory of that. In any case, these are the three basic commutators. In addition to that, we have operators that we can characterize as spin operators, namely the alpha and beta. They're purely spin operators. They don't involve any space-time dependence. And they commute with any purely spatial operator, which includes position x, momentum p, or kinetic momentum pi. They're all purely spatial. So we have basically x vector, p vector, or pi vector all commute with the alpha and the beta. Those commutators are all zero because they act on different degrees of freedom effectively. All right. So with that preparation then, let's look at the Heisenberg equations of motion. Let's compute the time derivative, let's say the ith component of x. According to Heisenberg, this is 1 over IH bar times the commutator of xi with the Hamiltonian. Now the Hamiltonian has three terms. The x vector here commutes with the last term mc squared beta because mc squared is just a constant, and beta is purely spin, and x is purely spatial. It also commutes with q phi because phi, the scalar potential, is a function of x, and x commutes with itself. So the only term that it doesn't commute with is the first term here. So this becomes 1 over IH bar times the commutator of, let me write it as alpha dot, as x sub I, and then the alpha dot pi, and there's a factor of c that comes out. And the alpha dot pi, let me write this as alpha j pi j. All right. Now, this commutator is easy because x commutes with alpha, so you can bring the alpha out of the commutator. This is alpha j times the commutator of xi with pi j. And by our table up above here, this becomes alpha j times IH bar times Kronecker delta ij, which is equal to IH bar alpha sub I. Then the IH bar denominator here and the IH bar numerator up there cancel, and what we end up with is that xi dot is equal to, the c still remains here. We have c times alpha sub I, or to write this out a little more compactly, let's write x vector dot is equal to c times alpha vector, and this we can define as being the velocity operator for the Dirac theory. Let me box that because that's an important result. Now, so this is the result for the velocity operator in the Dirac theory. This was including interaction with an electromagnetic field. This is a very strange result because, as you can see, the velocity operator is a purely spin operator. You probably would have thought it should turn out to be a spatial operator. In fact, in the non-relativistic theory, whether it's quantum mechanics or classical mechanics, the velocity is given by the momentum p divided by the mass. True in both cases. The velocity is a function of the momentum and is therefore a purely spatial operator. Likewise, in the relativistic but classical mechanics, we can solve for the velocity as a function of the momentum, and the answer turns out to be c squared p divided by the energy E, which if I write it out explicitly is c squared p, the momentum p, divided by the square root of m squared c to the fourth plus c squared p squared. This is the relativistic expression for the velocity in terms of the momentum. And again, it makes the velocity a function of the momentum, and we might have expected something like that in a relativistic quantum theory. But no, instead what we get is we get c times alpha. The alpha then is, remember, alpha is dimensionless, and we set it up to be dimensionless. That's why we split off a factor of c. So the velocity is a speed of light times a dimensionless vector of matrices, of Dirac matrix, 4x4 Dirac matrices, a collection of 3 of them. This needs interpretation, and it's going to take some, it'll take some time. This will play out over the next several lectures. You'll see how this works. But in any case, it's true, as strange as it seems, and it has some very strange consequences that follow from it. Here's one of them. You'll recall that the components of alpha, the matrices alpha, take one of them, call it alpha sub k. You'll recall that its eigenvalues are plus or minus 1. That's because the matrix squares to give you the identity matrix. The eigenvalues of all of the Dirac matrices are plus or minus 1. Therefore, if we take a component of the velocity, let's say v sub z, and we ask for what are the possible values when we measure the velocity of our particle, what values do we get? Well, of course, you get the eigenvalues of the operator. But the eigenvalues of v sub z are equal to c times plus or minus 1. In other words, in the Dirac theory, if you measure the velocity of your particle, the answer can only turn, if you measure one component of the velocity of the particle, any one component, the answer can only turn out to be plus or minus the speed of light. Now, isn't that weird? Here's something else funny too. The different components of velocity don't commute with each other because the different alpha matrices don't commute with each other either. The components of the momentum do commute because they're just the usual derivative operators, but not the velocity. Okay, so this means that it's impossible to find a state which is in an eigenstate, simultaneous eigenstate of all three components of velocity, unlike the non-relativistic theory. All right, strange features of the velocity operator. Now then, what about the momentum? Let's look at the equation of motion for, let's say, one of the components of the kinetic momentum, pi I dot. This is, of course, by Heisenberg equations of motion is 1 over IH bar times the commutator of pi I with a Hamiltonian. But we have to add the term partial of pi I with respect to t, because pi contains an explicit time dependence up here. You can see it has the vector potential in there, which depends on time. So this last term here turns into minus q over c times the derivative of the vector potential a sub I, its ith component, with respect to time t. All right. Now then, the first commutator here, pi I with h, let's look at that. So pi, the three terms in the Hamiltonian are given up here. The pi commutes with the last one because the beta is purely spin and pi is purely spatial. So the last term doesn't contribute to the commutator. Pi, however, does not commute with q phi because phi depends on x, nor does it commute with alpha dot pi because pi doesn't commute with itself. Here's the commutators for pi right up here. It doesn't commute with it. It commutes with alpha, all right, because pi is spatial and alpha is spin, but it doesn't commute with itself. So we need to work out what this commutator is. It's going to have two terms. It's going to have pi I. There's a factor of c that comes out. And then we have alpha j pi j. And then there's another term where a factor of q comes out, and we've got pi I commutator with phi, which is a function of x and t. Now this second commutator is slightly easier. This turns into, using the commutation relations for pi and x, this turns into minus q times IH bar times the partial of phi with respect to xi. This commutator, the alpha commutes with the pi, so it can be taken out. This becomes alpha j times the commutator of pi I with pi j, like this. And this becomes alpha j times IH bar q over c times epsilon ijk times b sub k, the magnetic field, from the commutator of the pi's. Now the alpha j over c is the component of the velocity, the jth component of the velocity. So this can be written as IH bar q times epsilon ijk times v sub k times, v sub j times bk. And this is equal to, if I have room to write it down, IH bar q times v cross b, the ith component of that. We get a term in v cross b. And so I'll omit the details of the rest of the algebra. It's straightforward. You can see the electric field is appearing here. There's a gradient of phi, and there's a derivative of the vector potential. When you work this out in the rest of it in detail and put the pieces together, then here's what we get. We get equations of motion that look like this. We get the velocity v, which is equal to x dot is equal to c alpha. I mentioned that already. And what we get is that pi dot is equal to the charge q multiplying onto the electric field, which is evaluated at x and t, plus the velocity v over c crossed into the magnetic field, evaluated at x and t. And this, of course, is exactly in the same form as the Newton-Lorentz equations of motion for a charged particle in a given electromagnetic field in relativity theory. I hope you're familiar with how it works in relativity. This is the time rate of change of the kinetic momentum, and it's given by the force, and that's what that is. So this is relativistic mechanics, and it comes out right. However, to make it come out right, the velocity that appears here is this spinner operator. It's C alpha crossed into the magnetic field, which is kind of strange, but that's what it is. At least it's consistent in how the velocity appears. All right. Now, amongst other things, what these Heisenberg equations of motion mean is that if you have a wave packet in the Dirac theory, that in an Ehrenfest sense, that if you want to make the wave packet localized, we talked about this last semester, it means that the wave packet follows the classical equations of motion, which now in this case are the correct relativistic equations of motion of a charged particle in an electromagnetic field. So all of this is good news for this for Dirac's program of understanding this equation, which he pulled out in the manner that I've explained. All right. By the way, there's one more comment about this velocity, strange velocity operator being the spinner operator. If we take the current, the non-relativistic current in the Schrodinger theory, this you may recall is the real part of psi times the velocity operator, psi star, the velocity operator psi star times psi on the other side, where the velocity operator would be just simply minus I h bar gradient over m if we were talking about a kinetic plus potential Hamiltonian. But if there were a magnetic field around, there'd be also the vector potential correction. In any case, you have to put in the real part here because otherwise the right-hand side is not real. But that turns out to be the current in this case. So it's more or less something that looks like a spinner expectation value of the velocity operator. This is not a full expectation value because you don't integrate over x. It's just a spinner well, actually, for a scalar wave function, there's not even any spinner contractions that you just get that. If you had a particle with spin, it would be the psi dagger velocity operator psi like this, the real part of that, and then you do have spinner contractions on this. So in the Dirac, whereas in the Dirac theory, we've got J is equal to psi dagger sandwiched around C alpha times psi, like that. That's what came out of our analysis of the probability current. Well, look, if we interpret C alpha as the velocity, again, it's the same thing. It's psi dagger psi sandwiched around the velocity. So again, as I say, it may be a strange notion for a velocity operator, but at least it's consistent. Everywhere you expect to see a velocity, you get a C alpha. All right. The velocity operator leads to the funny velocity operator leads to the notion of the Zitterbewegung, which we may or may not have time to talk about later in the course. It's too bad we don't have a few extra weeks in this course. We could cover some really interesting material. All right, that's all I want to say about the Heisenberg equations of motion. Are there any questions about that before I go on? If not, then the next topic is the non-relativistic limit. If you're going to go around inventing theories, relativistic theories, to invent new physics, you better make sure that it agrees with the known non-relativistic physics, assuming that is known, because otherwise it can't possibly be right. So we have to do this for the Dirac equation. In effect, we have to show that it is, in some approximation at least, that it reduces to the non-relativistic theory. So let's take a look at how we do that. So of course, one way of describing the non-relativistic limit is to say that V over C is much less than 1. I'm going to choose an alternative method, however. I'm going to say that the total energy is equal to mc squared plus a small correction, where the small correction is an energy which is typically of non-relativistic meaning. like a non-relativistic kinetic energy or potential energy, for example. We'll make this assumption.
I have a question.
Yes.
How would you even try and approach v over c much less than 1 if the velocity operator can only give you c in every component?
So that's, well, actually, I'm not doing that. You see, I'm using energies instead.
Right, but if you, is that like the main reason, or is there even a way to try and do small velocity limit?
Well, there is, but it's better to work with a momentum. What you should work with is a pi, which is the kinetic momentum over mc. That's the quantity you really should work with.
Okay, that makes sense.
And then this will be much less than 1. Of course, pi is an operator, but it means its expectation values will be much less than 1.
Right.
As far as expectation values of the velocity operator, which give you large things, we'll get back to that later on. We'll see what happens with that. But anyway, let's approach it from this standpoint, talking about energies, and then we don't have to worry about velocity funny business. All right. Now then, the Dirac wave function psi then has a time dependence, and assuming the energy has this form, it means that psi can be expanded as a linear combination of energy eigenstates, in which all of the energy eigenstates have an energy which is of this form. That's to say, it's mc squared plus small corrections. So therefore, the total time dependence of psi goes like e to the minus psi mc squared plus a small correction. Therefore, let's write the psi as a 4-component spinner. Let's write psi. Let's write it this way. Let's split off a factor of e to the minus psi mc squared t over h bar, removing the large component to the energy. And what's left over, let's break it up into two component spinners that I'll call phi and chi, lowercase phi and chi. The uppercase phi, by the way, I'm using that symbol for the scalar potential. Here, don't confuse it with lowercase phi, which is going to be the upper 2 components of the Dirac spinner. All right, so let's do this. Then we'll just plug this into the Dirac equation. So on the left-hand side, we got IH bar ddt d psi dt, and that's equal to this factor of e to the minus I mc squared t over h bar will come out. And then what's left is we get one term by the chain rule, the IH bar ddt applying to this phase factor gives me mc squared. And then there's a plus IH bar ddt. And then this acts on the new spinner, which is phi chi, like this, split into 2 parts. This then is equal to the right-hand side of the Dirac equation. I'm going to do this, by the way. Did I say this? I'm going to do this non-relativistic limit, including an electromagnetic field. So that means that our Hamiltonian is given back up here. C alpha dotted into pi plus q phi plus mc squared beta, where pi is, let me box it here. Here's what I'm drawing attention to. So I hope you remember what that looks like, because I'm going to put it out here. So the first term then is going to be, first of all, is a common factor of e to the minus I mc squared t over h bar that comes out. And then we have 3 terms. And the first one is a c alpha dotted into pi. But I'm going to write this as c like this. And then the alpha dotted into pi, I'm going to write it as a matrix. It's going to be c sigma dotted into pi on the off diagonal elements, and 0 like this. This is alpha dotted into pi. That's what that is alpha dotted into pi. This then multiplies onto phi chi. So that's the first term. Then and that pi includes the vector potential. Then we get q times the scalar potential multiplying onto phi chi. And then we get plus mc squared times beta, which is a matrix is 0, 1, 0, minus 1, multiplying onto phi chi, like so, and close it. All right. So having done that, I'll delineate it with two broad lines. What we've got is the Dirac equation with no approximations. It's just been written out in this form and splitting off this time dependent factor. This time dependent factor then cancels out, and we can now break this up into two component spinner equations. So allow me to do that. So the first equation is going to be, if I read across the first row here, is I get mc squared times phi from there, plus IH bar partial phi with respect to t from this term equals, the first term over here is going to be c times sigma dotted into pi multiplied onto chi, off diagonal element, you see multiplication here, plus q times capital phi times lowercase phi from here, plus mc squared, the upper component of beta is 1, so that's just times phi. For the lower component, I get mc squared times chi from here, plus ih bar partial of chi with respect to t is equal to c sigma dotted into pi multiplying onto phi, now taking the second row here, you see, plus q times capital phi times chi minus mc squared times chi because of the minus sign in the beta matrix over here. All right. Now then, we can clean up the phi equation because the mc squared phi cancels on the two sides. And the chi equation, I can clean that up too by bringing this mc squared chi over to the other side, whereupon it doubles because of this, the minus sign over here. So let me remove it there and put a factor of 2 over there, okay? Now then, the chi equation now has 1, 2, 3, 4 terms. One of them involves phi and the other 3 involve chi. Let's look at the terms that involve chi. There is this term, let's look at this term first. It's q phi times chi. Q phi is the potential. Obviously, it's a scalar potential. We're assuming the energy, as I just mentioned, is equal to mc squared plus a small correction. So let's think about a typical non-relativistic situation, like a particle is moving around in a potential energy, and as time evolves, energy trades back and forth between the potential and the kinetic energy. So both of those then are non-relativistic. They're of the same order of magnitude, which is the 1/2 mv squared, the non-relativistic kinetic energy. If that's the case, then going back down to our chi equation, it means that this term is much less than the mc squared chi term, which is a much higher energy scale. So this term can be neglected in comparison to the last term. Likewise, if I look at the ih bar d chi dt over here, this brings down the energy of the system, but it's only the small correction, not the full energy, because we already stripped off the mc squared. So this is also of the order of magnitude. The order of magnitude of this time derivative is equal to the small energy correction, non-relativistic energy, multiplying times chi. And again, that's also much less than the relativistic energy we see over there. So dropping those two terms, which is something valid to order v over c squared, we can now solve for the spinner chi here. Chi then, in terms of the spinner phi, chi then becomes equal to 1 over 2 mc times sigma dotted into pi multiplied onto the chi spinner. Onto the phi spinner. Let me write that way carefully. Let me box that because that's the relationship between the two spinners. Now, then let's take this thing and let's plug it back into the upper equation, the phi equation, and see what we get. It's very interesting how it works out. Bring it down some so you can see what I'm doing. So what we're going to get when I plug that in is I get from here, ih bar d phi dt is equal to, from this term here, 1 over 2 mc, the c's will cancel, I get 1 over 2m times sigma dotted into pi, quantity squared. And then we get a plus q phi times, this should be multiplied times phi here, excuse me. Then we get a q capital phi multiplying onto phi. And then we get, that's it, that's all there is. These are the two terms that appear on the right-hand side of the phi equation. All right. Now let's analyze this sigma dot pi squared. We're now dealing with 2-component Pauli spinners, not 4-component spinners, because this is now sigma is a 2x2 matrix. Let's look at this. Let's write this as sigma I pi I times sigma j pi j using index notation. Now sigma is a purely spin operation and pi is purely spatial, so we can rearrange them. The sigma doesn't commute with sigma, but it does commute with pi. So we can arrange this as sigma I times sigma j times pi j. But sigma j by the algebra of the Pauli matrices is Kronecker delta ij. plus I epsilon ijk sigma k. And this is then multiplying onto pi I pi j. And of these, the first term with the Kronecker delta just gives me pi vector squared. And as far as the second term is concerned, let's take a look at it. We've got an epsilon here contracted with pi I pi j. The epsilon is antisymmetric in the indices I and j. So we might as well project out the antisymmetric part of the pi product. And so the second term can be written this way as I over 2 times epsilon ijk times sigma sub k times the quantity pi I pi j minus pi j pi I. But that's the commutator of pi I with pi j, and we've seen that's equal to IH bar times Q over C times epsilon ij L B sub L. I'm using an index L because I've already used index K over here. All right. And so we get pi squared. Let's clean this up here. You see, there's two i's give us a -1, so it's going to be a minus sign. There's a factor of 2 here. There's two epsilons here. You've got epsilon ijk times epsilon ijl. And if you look at your epsilon identities, this is twice the Kronecker delta K and L. And so these epsilons go away and get replaced by Kronecker delta K and L, which gives you a contraction between sigma and B with a factor of 2. So what we get is taking care of the I times I is -1. There's a factor of a half here. I'll copy that, copy this here, I'll just run through it. Then we get H bar Q here over C. And then this is then multiplied times 2 times the Pauli matrices sigma dotted into the magnetic field. This is what we get. Now then, in the Hamiltonian, we need sigma dot pi squared divided by 2m. There's an effect, you see, there's effective Pauli, excuse me. It turns out to be a Pauli Hamiltonian, but I haven't shown that. It's effective Hamiltonian of a 2-component spinner now. It's 1 over 2m sigma dot pi squared plus q phi. And it's this Hamiltonian which I'm working out by doing this commutator. So I need to divide by this thing by 2m. And so for the first term, what we get then is pi squared over 2m. Am I still on screen? Yeah, let me move it up a little bit. Pi squared over 2m minus the 2 here will cancel with that. We get minus h bar q over 2mc times sigma dotted into the magnetic field B. Now let's analyze this and be careful about factors of 2. If I take h bar sigma here and divide by 2 and multiply by 2, then the h bar sigma over 2 is the spin. And this 2 cancels with that. So this term then becomes, including the minus sign, becomes minus q over mc times the spin dotted into the magnetic field B. Let me divide the spin by h bar and multiply this by h bar. Because if I do, then you see what appears here is, well, it would be a magneton except for a factor of 2. Let me put a factor of 2 and a factor of 2 there. So this becomes in -2 times a magneton, which I'll call mu0, times the spin over h bar dotted into the magnetic field, where mu0 is equal to the charge of the particle q times h bar over 2mc. And then this 2 here obviously must be interpreted as a g factor. You get g equals 2. So the net effect of this is that we achieve an equation which is the Pauli equation. It's IH bar partial of phi with respect to t is equal to 1 over 2m. The pi squared is the same thing as p minus q over c, a squared. Then what we get is with a minus sign, we get a minus mu dotted into the magnetic field plus the q phi, where the mu is equal to the g factor times the charge q, h bar over 2mc, times the spin divided by h bar. Okay. So what we've shown is that the by eliminating the lower component. Now, this is in the special case that the energy is essentially not mc squared plus a non-relativistic correction. We've shown that the solution of the Dirac equation, approximately anyway, to good approximation, can be thought of this way: as the upper two components are solutions of the Pauli equation within the same electromagnetic field, including the interaction with the magnetic field by the correction to the momentum term here in the kinetic energy, which we're quite familiar with, but also the interaction of the spin in the magnetic field with a G factor equal to 2. Meanwhile, the lower two components are given in terms of the upper two components by a formula that was on the last page. I'll bring it back, which is right here. If you want to know what those are, here they are. You can work that out. All right. So this gives us then a pretty complete description of the non-relativistic limit, or the low velocity limit, of the Dirac equation. And you see it reproduces the Pauli equation. It reproduces the Pauli equation for a particle of spin 1/2 and a G factor of 2. Now, this means that we're obviously talking about the electron. Without starting out thinking that our particle was going to be an electron, you see, we just follow this logic. We end up with the electrons clearly coming out. The electron G factor is not exactly 2, but it's close enough for our purposes tonight. Let's just say that this is compelling evidence that we got a theory of the electron here. And this is how Dirac interpreted it, of course. In the non-relativistic theory, G factors are just fudge factors that have to be put in by hand. You have to measure them, is what you have to do, and then put them in by hand. And but notably, if you do that, you find experimentally the G factor of the electron is very close to 2, which suggesting that there ought to be some simple theory that gives that. Well, now we see what that theory is. It's a Dirac equation with the assumptions that were made going into it, including the assumption of minimal coupling. We chose the simplest representation of the Dirac matrices, which made them 4 by 4. And as we see now, that implies a 2-component Pauli spinor as a non-relativistic limit. And we chose minimal coupling for the interaction with the field, and we see that leads to a G factor of 2. So minimal coupling is the simplest and cleanest interaction with the electromagnetic field. And that's where the G factor of 2 comes from, sometimes called the Dirac value. This development doesn't work for a particle like the spin-1/2 particle like the proton or the neutron, which has, as we say, anomalous magnetic moments. And the reason is that those particles require a non-minimal coupling with the electromagnetic field, and we may see some of that you may see this in a homework problem coming up, depends whether I give it or not. But anyway, it's in one of the homework problems, is to study the proton and neutron. All right. This is really a remarkable success of the Dirac equation, getting the G factor right. And oh, by the way, in the non-relativistic theory, we had to put in the mu dot B term by waving our hands and saying, well, we know there's an energy of orientation, so it ought to be in there, right? So what we see now is it comes out in the process of taking the non-relativistic limit. Notice that in the original Dirac equation that we started with, wherever it was, the original Dirac Hamiltonian, we'll go back to it here. There is no mu dot B term in there. Dirac didn't put it in. It wasn't necessary. It wasn't a part of minimal coupling. But by putting in minimal coupling, it turns out implicitly the mu dot B term has actually now been included, as I've just shown. By the way, you may wonder about higher order corrections like the fine structure and the relativistic kinetic energy and the Darwin term. What about them? Well, we made an approximation in this derivation I just went through, leading to the Pauli equation. You remember the approximations of dropping terms. If you go back to those and you take those into account in a more careful way and carry this all out to the next order of V over C squared, what you find appearing miraculously is all 3 of the fine structure terms. And what's most amazing about that is that in the spin orbit term, you actually get the factor of 2 from Thomas precession, comes out automatically from the Dirac equation. So the Dirac equation knows about Thomas precession. It knows about, in effect, it knows about the non-commuting boosts that take place as the electron goes around its orbit And because they don't commute, it generates a rotation, and that rotation cancels half of the mu dot B precession that you would have expected otherwise. That whole story, that whole complicated story that you see in the non-relativistic theory is automatically taken care of by the original minimal coupling Dirac equation. Okay, it's really a pretty result. Okay, so this finishes the current phase of the work on the Dirac equation. Let me ask if there's any questions. All right, if there's no questions, then we'll move on to the next phase. The next phase is to study how the Dirac equation transforms under Lorentz transformations. This is going to be necessary to show that the forecurrent, nominal forecurrent, actually does transform as a four vector. We'll see this, but it also leads to it's also a basic property of the Dirac equation, and is important for innumerable applications of the equation and understanding what it means. So I'm going to take this in two steps. The first is to cover some material from, if you like, classical relativity theory. I'm sorry that my light there's a light, which is my room light, and I see that it's throbbing. Is that annoying you? It's not on the page here. It's just in the background of my. I'm reluctant to turn off the room light because it's the main source of illumination here. I hope that's all right. Anyway, if that bothers you, let me know. All right. In any case, as I was saying, I want to undertake I want to put the quantum mechanics on hold and the Dirac equation on hold, and undertake a digression into just Lorentz transformations and special relativity, which could just be purely classical if you want, in order to make some points that and develop some material that we'll need later on for studying how the Dirac equation transforms. So let me make a beginning on that. There are some pages here. So let's talk classical special relativity. I'm just going to cover the parts that I need for what we need for the Dirac equation. Allow me to begin by making a sketch of a Lorentz frame in space-time. We have a time axis here, which I'll call T, and then we've got three orthogonal space axes, X, Y, and I'll make the Y and the Z axes coincide because we can't draw four axes in one on a page like this. And let's say this is a Lorentz frame. Then I think you know about the light cone. There's what you call a forward light cone, which can be sketched this way. And the physical meaning of it is that you imagine that there's a flash of light that takes place at the origin of the coordinates x equals y equals z equals 0 at time t equals 0, producing an expanding shell of light moving outwards at the speed of light. And the set of space-time events of the surface of that shell is sketched here as a cone. This cone expands as time goes up. This is the forward light cone. Likewise, there's a backward light cone, which is the backwards image of this. It looks like this. The backward light cone can be thought of as the surface of the cone can be thought of as the locus of events which lie on a contracting spherical shell of light, a pulse of light, which is contracting inwards, moving inwards at the speed of light, and comes to a focus at the origin of the coordinates at time t equals 0, making that point there. That's the backward light cone. I hope you also understand the causality implications of all of this, is that the set of events that are inside the forward light cone or inside well, let's take the forward light cone first. The set of events inside the forward light cone are events that are causally connected with the origin, the vertex of the cone. That is to say, any such event, such as the tip of that arrow there, can be reached from this event by means of particles or information transfer that moves at velocities less than or equal to the speed of light. This includes also on the surface of the forward light cone as well, because you can move at the speed of light. So this is the causal future of the vertex of the cone. Likewise, the causal past of the vertex of the cone is a set of events in the lower light cone, which can be connected by particle orbits moving again less than or equal to the speed of light, connecting those events with the vertex. On the other hand, events which are outside the light cone are causally disconnected. That means that there can be no causal influence between any event outside the light cone and the event at the vertex. Okay. Now the equation of the cone, of the light cone, is that c squared t squared is equal to x squared plus y squared plus z squared. That's the equation of the cone, which is revealing the a version of the relativistic invariant. Let's talk about some event out here. Let me call the event with, let's say it has coordinates x mu. I'm using the same notation introduced earlier. X mu is the space-time coordinates. The time component is ct. The spatial coordinates are the usual Euclidean coordinates x, like this. Let's take an event out there and visualize it as a vector in space-time connecting us from the origin. And maybe we have another event, x prime out here like this, x prime mu. We can have events like this. In general, if there are two events in space-time, let me draw them here as two events in space-time with a connection between them, which gives coordinate increments, let me call it delta x mu in our Lorentz frame. Then we can construct the relativistic invariant, which is delta x mu sandwiched around g mu nu, the metric tensor, delta x nu. The metric tensor I've introduced before, but I'll give it to you again. It's +1, -1, -1, -1. It's the usual metric tensor that's used in special relativity, and I'm following Jackson's conventions here. In any case, this I is the invariant interval connecting these two space-time events. And it is a statement of relativity that this I has the same form in all Lorentz frames, which means if I go to a new Lorentz frame, that if I put primes on the delta x's to indicate the transformation to the new frame, then the value of this quantity is the same. I equals, let's call it I prime. I and I prime are the same. If we talk about an interval from the origin of the cone to events elsewhere in space-time, then the events which are inside the forward light cone have an I value, or in the backward light cone, they have an I value which is positive, corresponding to what we call time-like intervals. If it's on the light cone, we've got I equals 0, and those are light-like intervals, because that's the equation of the light cone. This interval is equal to 0. And if I is negative, we have space-like events, or space-like separation between events. Okay. Now then, allow me to consider a mapping of space-time into itself that takes our event x mu into the event x prime mu. Let's call this mapping lambda, call it capital lambda here. So the idea is we want a mapping of space-time onto itself, which does this. It takes x mu, according to lambda, into x prime mu. We want this mapping to be a linear mapping, so we can write it in terms of a matrix. X prime mu is equal to lambda mu nu, like this, x nu. We require linear mappings because only a linear map maps straight line orbits at constant velocity into other straight line orbits with constant velocity. And the physical idea behind a Lorentz transformation is that it's a frame in which free particles, i.e. particles upon which no force acts, follow trajectories which are straight lines with constant velocity. That's a characterization of a Lorentz frame. And so if you go from one Lorentz frame to another, that characterization must be preserved. And the way to do that is to use linear transformations among the four coordinates. In any case, we'll make such a linear transformation. Now, I will now define a Lorentz transformation. A Lorentz transformation, lambda, satisfies the property that the invariant I is the quantity I, which I'm calling an invariant, actually is an invariant. In other words, let me write this way, is x prime mu times g mu nu times x prime nu is equal to, let's write it as x alpha times g alpha beta times x beta. All right. So this is a definition of a Lorentz transformation for the purposes of this course. This is kind of backwards to what you probably did in your introductory course on special relativity. In an introductory course, the usual procedure is to work out the Lorentz transformation for a boost using the assumption that the speed of light is constant and space is homogeneous and so on. This is basically Einstein's argument in the derivation of the Lorentz transformation. It's the same as the original argument in his 1905 paper. And it gives you a specific explicit form for the Lorentz transformation, which if you're only changing two coordinates just amounts to a 2x2 matrix. Once you've determined that Lorentz transformation, however, you can then verify that this quantity I really isn't invariant. That's something you can just check and see. Now, what I'm doing is I'm turning things around. Instead of working out Lorentz transformations and verifying that I isn't invariant, I'm going to say that here's I. I'm going to require, I'm going to define a Lorentz transformation as a linear transformation that leaves this invariant. This has the advantage of uniting Lorentz transformations such as boosts with the full set of Lorentz transformations, which includes not only boosts, but also rotations and also discrete operations such as parity and time reversal. So I want to say some things about that now. That's the reason I'm approaching it from this standpoint. If we take this requirement on the Lorentz transformation, and I plug in our formula up here for x prime in terms is basically lambda x, and plug that in here, there, and here over here, then what we get is the following equation. We can write this way as x alpha times lambda mu alpha times g mu nu times lambda nu beta times x beta is equal to the right-hand side x alpha g alpha beta x beta. By the way, I didn't say this, but the matrix lambda here, I'm writing this, as you can see, I'm writing it as a lambda. I'll write it big so you can see the first index upper and the second index lower with a little dot there. The dot is nothing but a placeholder. It's a way of keeping the nu from sliding under there and confusing you about which index comes first. The mu index is first, and it's an upper or contravariant index, and the nu index comes second, which in this case being a lower index is a covariant index. So that's the notation here. All right. In any case, this has to be true for all values of x mu, all points in space time, which appears there and there and there and there, x alpha and x beta. And so the matrices in the middle, which are here and here, they're both symmetric matrices, must be equal. And therefore, a Lorentz transformation satisfies the equation that lambda mu alpha times g mu nu times lambda nu beta is equal to g alpha beta. That defines a Lorentz transformation. All right. Now, it's convenient to put this into matrix form. We'll do it this way. Let's let G equal the matrix with components G mu nu, lower indices. Then let's let G inverse be the matrix with components G upper mu nu. And let's let lambda be the matrix with components lambda with the first index upper and the second index lower. The first and second indices here always correspond to rows and columns if you want to put this in the form of a matrix. So that's what I've done here. Now, if we do this, and we can take the condition on a Lorentz transformation and write it in matrix language, it turns into this. Let me write it as a statement. Lambda is a LT means Lorentz transformation. If lambda transpose, that's the first matrix here, times G is the second matrix, times lambda is equal to G. So let me box that because this will be the most compact and convenient definition of a Lorentz transformation that we'll be using. All right. I invite you to compare this to what we did with spatial rotations last semester. you can say that you can say the matrix R, 3 by 3 matrix R. Of course, these lambdas are 4 by 4 matrices. 3 by 3 matrix R is a rotation if R transpose times the identity times R is equal to the identity. And if this is the case, then we say that R belongs to the set of 3 by 3 matrices we call O3, which happens to form a group. It's a 3 by 3 orthogonal group of orthogonal matrices. Likewise, if we compare this to the formula we got for the Lorentz transformation, you can see that the Lorentz transformation, in a sense, is a matrix that's orthogonal, but it's not with respect to the Euclidean metric indicated by the identity over here, but rather with respect to the Minkowski metric, which is this metric G. As a result, if a lambda matrix satisfies this equation, we say that lambda belongs to the set O of 3, 1, where the 3, 1 means this notation means matrices that are orthogonal with respect to a metric which has 3 space-like and 1 time-like dimensions. So that's just notation, but that's what it means. Now it's easy enough to show that this set O3, 1 actually forms a group. You just run through the axioms of the group and run it against this definition, and you can check it to see. It's actually outlined in the notes, but it's a good idea for you to just to go through it if you've never done it before, as a simple exercise. In any case, this item is a group, and that introduces us to the Lorentz group, which is the group O3, 1. It turns out it's a generalization of the spatial rotation group O3. I'm really just about out of time, but let me just preview the next couple of steps. You may recall last semester when we dealt with rotations, we split them into proper and improper rotations, depending on whether the rotation contained, in effect, a spatial inversion or parity operation. And that split it into 2 parts. And then we talked about the proper rotations being ones that don't involve parity. Well, likewise, the O3, 1 can be separated not into 2 subsets, but rather 4 subsets. And this is related to whether or not the operation contains a parity operation or spatial inversion, or whether it contains a time reversal operation, one or the other or both. And the combination, all possible combinations then give us 4 different, as we say, components to the group O3, 1. In other words, the discrete symmetries of parity and time reversal are contained in this definition of a Lorentz transformation. And having done that, I'm going to split the discrete symmetries off, and we'll be left over with what we'll call proper Lorentz transformations, and most of our effort will be focused on those. All right, so that's all for tonight. Are there any questions about this up to where we are? I'm going to stop the screen, share. One last call for questions. If not, I'll turn off the recording. All right, well then thank you for your attention, and I'll see you next Tuesday.